So we're about to go on to Euler's method, which is the last thing we're going to learn in this course. And before we go there, I want to kind of formalize something we've talked about in the past called linear approximation. And that's a fancy word for saying use the tangent line to approximate. For this example problem, I'm going to say approximate f of 1.4. We don't know anything about the function. We don't know the formula for the function. We just know that it's differentiable. And we know that f of 1 equals 4 and f prime of 1 equals 2. So if you said approximate f of 1.4, you would say, well, I can't approximate it. I really don't have a great idea where it is, but I can use the information that I do have, maybe come up with a number that's not too terrible of an estimate. I mean, we know it's not going to be perfect, right? But let's just say there's a 0.1 comma 4, and we know that the rate of change of the function, it's changing at 2. The y is changing right there at that point, 2 for every 1 change in x, right? So that's what the 2 is telling us. So if you said approximate f of 1.4, you could say, well, I don't know exactly what it is, but if I had to go out 0.4, my change in x was 0.4, I would guess my change in y is going to be 0.8, because 0.4 times 2 is 0.8. So if I'm at 4, I'm going to go up by about 0.8. I'm going to call it 4.8, and that's my best guess. Do I think it's perfect? Absolutely not, I don't. But hey, it's approximation. And really what we're doing is we're saying this, folks. We're saying that we're going to say that f of x plus some change in x is going to be f of x plus some delta x times the slope. And this is kind of a formalization. Don't write that in pen because I'm going to change something in a second for you. And that's kind of what we're saying, right? And we've kind of seen this before. I mean, some of you will say, that kind of looks familiar. Yeah, it does look familiar, right? If I just do a little bit of algebra, I'm going to leave the algebra for you folks at home. That's the same equation of that. And you might be saying, yeah, that is true, right? What is that? Well, that's the definition of the derivative. And that is true, but only when? This is only true as delta x goes to 0, folks. So it's only true if delta x is really, really, really small. And that's why this equation really shouldn't be an equation, right? That's why we have to make sure we're using the approximate symbol, right? We're approximating. And to be crystal clear, folks, what we did here is we just did this, right? I want to take you through this example. We did this. And that's how we got 4 plus 0.8. Okay, that's where the 4.8 came from. If we knew the actual value of function, we could know more, right? We could know whether we're high or we're low. If we knew the concavity, we could know if this 4.8 is too high or 4.8 is too low. Remember, if it's concave up, we know if the function is concave up, we know the 4.8 is too low. If the function is concave down, we would know that the 4.8 is too high, right? But we don't know anything about the concavity, so that's all we can do with linear approximation. Now, what we're going to do now, though, is use linear approximation in this new method called Euler's method. And Euler's method is a little bit different in that you, instead of doing it one big jump, we went from 1 to 1.4 in one big jump here. Euler's method says you do multiple steps, go in parts. So in this case, we're going to say go from, find approximate f of 1.1, using the data of f of 1, we're going to approximate f of 1.1. But this is a different problem, folks. I want to make sure this is a different problem. The numbers are all different. But here you're going to use 2 steps. That means you're not going to go from 1 to 1.4. We want you to kind of take one step and then another step. So to find out the step size is going to be your delta x. And to find your step size, what you do is you take the difference. Your 1.4 is what we're trying to approximate. 1 is what we know. So we say take the difference of what we're trying to approximate and the value that we know, the function value that we know the value of f of 1, and divide it by the number of steps. Right? That 2 here is this 2 here. And therefore, we know that our step size is going to be 0.2. Now, folks, all we're going to do is linear approximate twice. So we'll linear approximate 1.2. Okay. Using the same exact formula on the previous page. So therefore, we think f of 1.2 is going to be f of 1, which is 2, plus 0.2 times f prime of 1, which is, they didn't tell me f prime of 1. But they did give us this. And there's a reason they gave us that, folks. Because when you're doing Euler's method, you need to have the differential equation, because you can use this to figure out what the slope is at x equals 1. At x equals 1, what's the point? Well, the point we think is 1, 2. We know it's actually 1, 2. We know it's 1, 2. So we can come in here and say at 1, 2, the slope is going to be 1 plus 2 times the y coordinate, which is 2. So the slope is going to be 5. And I think, folks, that means we're going to get a nice approximation of 2 plus 1, which is 3. So we think f of 1.2 is 3. Is it 1? Is it 3? No, we don't know it's 3, but it's our best approximation. We're going to use that to figure out now what's f of 1.4. Well, f of 1.4, we're going to use now our best approximation of f of 1.2. We're doing this in 2 steps. This is our second step. What's f of 1.2? Well, we think it's 3. And that's a 0.2. You might not be able to see it, but it's 0.2. Well, what's f prime of 1.2? I don't know what f prime of 1.2 is. But I can tell you that if I think that point, right? Remember, I think the point is 1.2, 3, right? I think the point on this curve is 1.2, 3. I can use that information. So I'm plugging the 1.2 and the 3 into our formula here for dy dx. So dy dx at 1.2, 3 is going to be 1.2 plus 2 times 3. I think that's 7.2. That's what I think the slope is at that point. And what is that going to be? 1.44. 4.44. So I think f of 1.4 is 4.44. Is it? No, we don't know what it is, right? But we're just approximating. And the key thing for us to remember is we're using the data that we have in this differential equation to approximate. And really what we're doing, folks, is we're kind of saying, hey, let's go to this 1 point, just to kind of visualize what we're doing. We're saying, hey, here's where we are. And we want to figure out 1.4. But we're not going to jump there in 1. We're not going to linear approximate in 1. We're going to figure out the slope here to get some new point. And once we get that new point, this approximation of f of 1.2, we're going to use the slope there to get some new slope. And it's too messy. I'm upset with my handwriting here. But we're going to use this new point to find the new slope and therefore use that slope. So we're kind of going out one linear approximation and then another linear approximation. And the slopes are different here. This slope is the slope that we had of 5, and this slope is the 7.2 slope. We're using that for Euler's method. Euler's method is a fancy way of saying linear approximation multiple times. And the number of times you have to do it is dictated by the number of steps that they have to tell you in the problem. They have to tell you how many to do. Hope that made sense.